NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is now more mysterious and more beautiful than humanity's dreams. All these little dots are stars. All these little dots are galaxies, some of which are bigger than our own. Breaking news: we may have just found potential evidence of intelligent life beyond Earth. This is a huge discovery, and we think that it's a huge discovery. The most exciting part of this remarkable instrument we've put in space is finding things that we didn't expect and that we can't explain. This means we have to revise our understanding of the universe. The jwst is so phenomenal that if you spend enough time, you could probably find any galaxy that ever formed in the universe. It's really that powerful. Proxima Centauri, as you indicated, is the closest star to the Earth, and it has a planet orbiting around it. Proxima Centauri itself is part of a category of stars that is very common in the Milky Way galaxy, what we call a red dwarf. As a consequence, red dwarfs have become a focal point for searching for planets, and thus for looking for signs of life. The problem with red dwarf stars is that they are notoriously unstable in terms of flare activity. These flares can be deadly, much like the coronal mass ejections we sometimes experience on Earth. These types of stars give off harsh radiation that would be fatal to humans. This brings into question whether life could exist on Proxima B and, if so, whether it could survive. Astronomers are scrutinizing these environments to determine the chances of life existing on such planets. In this pursuit, we have uncovered crisp, clear pictures of Proxima B, an exoplanet dancing in the gravitational embrace of Proxima Centauri. Its discovery in 2016 unlocked new dimensions in astronomical exploration, and now, the clearest image of Proxima B, released by the James Webb Telescope, is here. It is a big deal, huge. Stick with us to see why it matters so much. Proxima Centauri is the closest known star to the Sun and was discovered in 1915 by the Scottish astronomer Robert Innes. He identified this red dwarf star as the closest member of the Alpha Centauri star system. A century later, in 2016, an international team of astronomers led by Guillaume Anglodescu discovered Proxima B, a celestial body orbiting Proxima Centauri, situated within the habitable zone of its star. This exoplanet sparked excitement upon its revelation, promising a potential glimpse into the cosmology of habitable worlds beyond our solar system. Unveiled through the lens of the James Webb Space Telescope, the significance of Proxima B extends far beyond its celestial presence, offering a tantalizing opportunity to explore the mysteries of distant worlds. The discovery of Proxima B was a watershed moment in astrophysics. Despite its closeness, technological limitations had hindered detailed exploration until the recent breakthrough. Equipped with cutting-edge imaging and spectroscopic tools, the James Webb Space Telescope has now offered astronomers the first-ever direct image of this Earth-sized exoplanet. The image is a big deal. It has not only expanded our understanding of neighboring celestial bodies but also sparked profound implications for scientific exploration beyond our solar system. This image represents a pivotal achievement, offering a visual insight into an exoplanet residing within the habitable zone of a nearby star. This breakthrough has fueled excitement within the scientific community, renewing the quest to comprehend the potential habitability of exoplanets and explore the prospects of life beyond our solar system. So how was the James Webb Space Telescope able to help us here? Positioned at the second Lagrange point, L2, approximately 1.5 million kilometers, about 1 million miles, away from Earth, the jwst is the pinnacle of our space-age inventions. This location allows it to maintain a stable orbit relative to our planet as it revolves around the Sun. Equipped with an array of advanced scientific instruments, the jwst can capture images and collect data across various wavelengths, especially in the infrared range. Its primary mirror is composed of 18 hexagonal segments and has a diameter of 6.5 meters, 21 feet. This is significantly larger than those of its predecessors. To picture exoplanets like Proxima B, the jwst utilizes its near-infrared camera, NIRCam, and near-infrared spectrograph, NIRSpec, among other instruments. The NIRCam is pivotal for imaging and detecting objects in the near-infrared spectrum, while NIRSpec performs spectroscopy to analyze the chemical composition, temperature, and other properties of celestial bodies. Given Proxima B's distance from Earth and the challenges of observing exoplanets, the JWST's capabilities are essential. Its infrared sensitivity allows it to detect the faint infrared light emitted by Proxima B, which is crucial for characterizing the planet, studying its atmosphere, and potentially identifying signs of habitability. The telescope's high resolution and sensitivity enable it to gather detailed information about exoplanets like Proxima B, contributing significantly to our understanding of these distant worlds. And it's been a long time coming. The JWST was preceded by the Hubble Space Telescope, HST, which stands as an icon in space exploration. Launched in 1990, the HST marked a significant leap in our understanding of the universe. Its journey traces back to the space race era of the 1950s and 1960s, a period characterized by intense competition between the United States and the Soviet Union. This rivalry extended beyond geopolitical conflicts and into the realms of science and technology, culminating in ambitious space programs. The origins of the Hubble can be traced to the aftermath of the space race, as space agencies sought to transcend the confines of Earth's atmosphere, which distorts and blocks much of the incoming light from celestial objects. NASA's response to the problem was simple. They envisioned a space-based observatory that would evade these atmospheric limitations and offer unprecedented clarity and precision in astronomical observations. However, upon its launch, a flaw in the Hubble's primary mirror compromised its initial capabilities. The mirror suffered from spherical aberration, causing images to be blurred. This reduced the telescope's effectiveness significantly and led to a major re-evaluation of the project, necessitating a groundbreaking repair mission in 1993, where astronauts installed corrective optics to rectify the mirror's flaw. Despite this early setback, Hubble went on to revolutionize our understanding of the cosmos. It conducted extensive surveys, including the Hubble Deep Field and the Ultra Deep Field, capturing images of incredibly distant galaxies and shedding light on the early universe's evolution. The HSD also provided detailed images of planets within our solar system, allowing scientists to study their atmospheres, weather patterns, and moons. The Hubble also observed stellar birth, evolution, and death, unveiling the intricate details of star-forming regions and planetary nebulae. Its observations contributed to measuring the rate of expansion of the universe, leading to the discovery of dark energy, an enigmatic force driving the universe's accelerated expansion. However, while revolutionary, the Hubble had limitations. Its instruments, although groundbreaking at the time, were based on technology from the 1970s and 1980s. Moreover, its location in low Earth orbit didn't shield it entirely from the planet's atmospheric disturbances. Naturally, the need for a successor arose. The James Webb Space Telescope was designed with larger and more advanced instruments, specifically optimized for infrared observations, enabling it to peer deeper into space. The study of the earliest galaxies and the characterization of exoplanets have advanced in ways the Hubble Space Telescope simply couldn't achieve. The James Webb Space Telescope, JWST, represents a new era in space exploration, building upon the legacy of the Hubble while pushing the boundaries of our understanding of the cosmos. With unprecedented clarity in cosmology and the study of exoplanets like Proxima B, the JWST has revolutionized our ability to explore distant worlds. Proxima B's orbit around its parent star, Proxima Centauri, is a captivating aspect of its characteristics. Despite its relative proximity to the red dwarf star, this exoplanet exists within the habitable zone, a region where conditions might allow for the presence of liquid water. However, its location in this zone does not mirror Earth's. Proxima B receives a significantly different energy intake compared to our planet, and this variation in energy absorption dramatically influences its climate, surface conditions, and overall habitability. The potential effects of this energy variance, whether it leads to extreme temperature fluctuations or unique atmospheric compositions, present intriguing avenues for further research and understanding. Proxima B resides within tantalizing reach at just 4.2 light-years away. Despite being Earth-sized and potentially habitable, It remained elusive because no telescope, ground-based or in space, possessed the prowess to directly photograph this distant world. The jwst is designed precisely for infrared observations and thus does not have to visually capture the planet. Instead, it focuses on specific infrared wavelengths, tracking the color changes of Proxima B as it orbits. This is a promising research area, and we have made many bold strides since the exoplanet's discovery in 2016. What truly distinguishes Proxima B is its brief orbital period. The exoplanet completes a full revolution around Proxima Centauri in a mere 11.2 Earth days. This short year raises compelling questions about the environment and the potential habitability of the planet. Such a swift orbit suggests that Proxima B likely experiences gravitational and tidal forces very different from those observed and felt here on Earth. These differences can shape its geology, weather patterns, and potential for retaining an atmosphere. Of course, there is still much to study about the planet, but how did we discover it in the first place? The discovery of Proxima B primarily stemmed from the radial velocity method, a sophisticated technique used to detect exoplanets by measuring the minute shifts in a star's spectrum caused by the gravitational tug of an orbiting planet. To better understand this approach, imagine a star and its planets dancing together through space. When a planet orbits a star, it doesn't just revolve around it, it also pulls the star slightly, causing both to move. This gravitational tug creates a wobble in the star's motion that we can detect from Earth. Scientists look for tiny changes in the star's light caused by this wobble to determine if there might be planets orbiting it. We have observed telltale signs within the light emitted by Proxima Centauri, indicating the presence of a relatively small Proxima B in orbit around it. This significant finding propels the exploration of exoplanets to new heights, spurring further investigations into Proxima B's atmospheric composition, surface features, and potential biosignatures. Understanding the intricacies of this neighboring exoplanet holds the promise of unveiling insights into the broader questions of habitability and the prevalence of life beyond our solar system. The remarkable aspect of this discovery lies in the fact that Proxima B occupies the habitable zone of its star, sparking tremendous enthusiasm within the scientific community. There is a possibility that this rocky planet may house conditions suitable for liquid water, an essential ingredient for the emergence and sustenance of life as we know it. However, the proximity of Proxima B to its parent star, Proxima Centauri, poses significant challenges for potential life on this exoplanet. Naturally, the planet is subjected to intense radiation from its star. This radiation bombardment can potentially alter its chemical composition and impact any potential biosphere. Understanding the extent of these effects requires intricate models that consider the interplay of radiation and the planetary environment. While the planet might possess an atmosphere capable of sustaining liquid water, its proximity to the star might result in extreme weather patterns, including fierce solar winds and potential atmospheric stripping due to the star's activity. These conditions could lead to an environment drastically different from Earth's, making it challenging for life to thrive. However, based on recent data from the jwst, we have deduced that the planet does indeed hold water vapor in its atmosphere. This is a significant discovery. Water is an essential ingredient for habitability, and understanding its presence or absence on this exoplanet is crucial. Current scientific models and observational tools, including spectroscopy and atmospheric modeling, have been employed to study Proxima B's atmosphere remotely. Spectroscopic analysis enables scientists to detect the composition of gases in the atmosphere, providing insights into the potential presence of life-supporting elements like oxygen, methane, or carbon dioxide. These tools, combined with advanced atmospheric modeling, offer glimpses into the planet's atmospheric conditions and help us formulate hypotheses regarding its habitability. Further advancements in observational techniques and modeling will be instrumental in unraveling the mysteries of Proxima B's potential to host life. The possibility of extraterrestrial life on the planet, despite the challenges, remains an exciting avenue of research. On Earth, extremophiles, organisms capable of surviving in extreme environments, provide a compelling case for life's adaptability. For instance, Pyrococcus furiosus thrives in deep-sea hydrothermal vents where temperatures exceed 100 degrees Celsius, Psychrophiles, on the other hand, flourish in freezing temperatures. For example, Psychrobacter arcticus can survive in Arctic and Antarctic environments. Similarly, acidophiles like Acidithiobacillus ferrooxidans thrive in highly acidic environments, while alkalophiles such as Natronomonas ferreones survive in highly alkaline conditions. Lastly, halophiles like Halobacterium salinarum live in highly saline environments such as salt flats, demonstrating resilience to extreme salt concentrations. Considering the potential conditions on Proxima B, where intense radiation due to proximity to its star might be a challenge, organisms like extremophiles on Earth may be able to adapt and perhaps even thrive. For example, Deinococcus radiodurans boasts resistance to ionizing radiation, surviving doses thousands of times higher than what would be lethal to humans. Extremophiles have evolved various adaptation strategies, including DNA repair mechanisms, protective pigments, and unique cell structures. These adaptations hint at potential survival mechanisms that life forms on Proxima B might develop to endure its harsh conditions. Discovering extremophile-like organisms on Proxima B, capable of surviving extreme radiation or other harsh environmental factors, would indeed revolutionize our understanding of life's adaptability beyond Earth. It could redefine the boundaries of habitability and widen the scope of exobiology, indicating that life might persist in seemingly hostile extraterrestrial environments. However, this is easier said than done. Exploring Proxima B and other distant exoplanets poses significant technological barriers. Currently, we are facing limitations in directly observing and characterizing distant celestial bodies. While telescopes like the James Webb Space Telescope offer invaluable insights, they have constraints in capturing detailed images or conducting on-site analysis due to vast distances and the limitations of available technology. Overcoming these limitations requires advancements in telescope design, sensor technology, and perhaps even the development of revolutionary propulsion systems to enable interstellar missions. Future technologies for interstellar exploration could revolutionize our capacity to explore and understand exoplanets like Proxima B. Concepts involving advanced propulsion systems, such as solar sails, ion propulsion, or even theoretical concepts like warp drives, are under study. These technologies aim to significantly reduce travel time to distant star systems, enabling closer observations and potentially even direct exploration of exoplanets. However, as of yet, these concepts are largely theoretical and necessitate extensive research.